The purpose of this video is to demonstrate how to interface a circuit created in hardware description language in a field programmable gate array to a PC. The PC commands can be script, or in this case, that can be generated by a GUI. These data commands are transferred over the USB to a modular firmware skeleton for multiple instruments. This LabTools code interfaces to an FTDI FT2232H USB interface chip, which can transfer data at the full USB 2 rate of 60 megabytes a second. This data goes to a USB 2 to addressed bus interface, which interfaces to three 8-bit buses, an 8-bit bank bus, an 8-bit address bus, and a bi-directional 8-bit data bus. These buses go to instrument modules. There are also a number of useful clocks. This level of the circuitry should also not need changing. Beyond, say, carrying clocks across, wiring between the instrument modules, and wiring the instrument modules up to the outside world. We have already discussed instruments 1 and 2 in previous videos. Instrument 1 contains 2 kilowords of 16-bit memory and is used as an example of transferring data at full USB 2 rates to and from the PC. Instrument 2 contains a binning algorithm which can eat the bytes from the bus at full USB 2 rates and can do it for longer data transfer lengths than just the default 64K length of a USB bus transfer. For this purpose, we use instruments 1 and 2 unchanged and add in instrument 0 a 16-bit counter and 16-bit comparator. Here we can see such circuitry as written in the Altera Quartus 2 graphical software. We have the 16-bit load data, we have a load command, we have an up-down command, we have the 1 Hz clock, we have a counter enable line, as well as an asynchronous line which resets the chip on power up. We have a 16-bit equality register which flags when the counter value is 0, and we're taking the counter output. We want to take the counter output back to the PC. How do we do this? How do we interface these lines, these 16-bit data lines to the PC? The answer is we use 5 of the 256 registers that are available in each instrument. We're going to use 2 registers as a 16-bit load word at address 8 and 9. We're going to use 2 registers to read the counter back at address 10 and 11, and at address 17 we can have an 8-bit control and status register. The 16-bit data is read to and from the circuit simultaneously and then transferred as separate 8 bits over the USB bus. Here we can see the bits of the control and status register. Bit 7 is the count enable, bit 2 is the count load, and bit 1 is count up. Bit 0 is a status bit for counter is 0. This then interfaces 2 similar bits in the GUI for instrument 0, as can be seen here. Here we see instrument 0 written against we can see how the bits line up: the enable bit, the load bit, the count up bit, and the status 0 bit. We can see the load data we can load, and we can see the count value. We have loaded the graphical user interface. It has established communication with the Morphic2 gate array and loaded the VHDL code into it. We will interact with instrument 0. This is a simple 16-bit counter with a control and status register with an enable bit, a load bit which loads this value, a count up down bit, the count appearing in this window, and an is equal to 0 status bit which lights this LED. If we run this code, we see we indeed do pull down the current value of the register, which is 0, and so the is status bit lights this LED. We can enable the counter. If we update the control and status register in the gate array, we see we indeed do start counting up. We can set it to count down, and we notice the LED has gone up because we're no longer 0. The count goes down, and as the count reaches 0, we see the LED will light again. We can load a value into the counter, and then we can resume counting. Instrument 1 contains a 2 kiloword block of 16-bit memory in the Field Programmable Gate Array. This is used to demonstrate transferring data at full USB 2 rates between the PC and the Field Programmable Gate Array. We will now use the graphical user interface to interact with instrument 1 in the gate array. This allows us to transfer data to and from a block of 2 kiloword 16-bit memory. We can choose our waveform and we can choose its length. We will generate the waveform and plot it, and then we will upload it, and we see that's taken about 21 milliseconds. Different uploads will take different lengths of time depending on how busy the PC otherwise is. We can now download from the 2 kiloword of memory, and we can plot that. We can change the length of the data array, generate a new waveform, plot it. When we upload this data, because we only have 2 kiloword of memory, it will cyclically overwrite. So the waveform, being the end of the final data set, looks the same when we download it, and taking about the same length of time as before. For those wishing to use script commands to transfer data between the PC and memory in the Field Programmable Gate Array, there's a video at YouTube, youtube.com/user/labtoolsinstruments. Instrument 2 contains firmware that executes a hardware binning algorithm. It can accept data from the USB 2 bus at full USB 2 rates for extended data lengths, longer than the standard 64 kbyte length of a USB transfer. We will now use the graphical user interface to interact with instrument 2 in the Field Programmable Gate Array. This contains a block of code that executes a hardware binning algorithm. This can eat codes sent to it over the USB 2 at full USB 2 rate indefinitely. We will generate a waveform. We have a number of possible distributions and a number of different lengths, and we will plot the random data that we've just generated. We will bin this in the hardware of the gate array, and we will see how long this takes. We can plot this data, and we can see, as expected, we get a normal or Gaussian distribution. Very noisy, because we did not send many data points. We can increase the number of points so that it's greater than will transfer in one standard USB data transfer of 64 kilobytes. If we generate this and plot it, we can now bin it in the gate array, and we can see that that has transferred successfully the individual 64K transfers being handled seamlessly. We can ask for a uniform distribution, generate that, plot it. Random noise looks a bit different. We can bin it and plot that, and as we see, we get a fairly uniform distribution. For those wishing to use script to transfer long blocks of data from the PC to firmware code in the Field Programmable Gate Array, there is already a video on YouTube at youtube.com/user/labtoolsinstruments. Code for this is available. The binary only is a free download to allow you to test the GUI and the firmware running in a Morphic 2 or similar Field Programmable Gate Array. This is available from LabTools. If you wish for source code so that you can modify it and use it for your own convenience, this is also available for both personal use and commercial use at very advantageous rates. The Morphic 2 FPGA modules are available from FTDI at ftdichip.com, and these are available from LabTools as well, mated to credit-sized card modules for data collection and instrumentation interfacing. This is at lab-tools.com.